Have you ever looked at a flat world map and wondered how something so smooth could representing our incredibly complex planet? Our Earth is a beautiful, three-dimensional sphere, or more accurately, an oblate spheroid, which means it bulges slightly at the equator and is flattened at the poles. When we try to take this curved surface and display it on a two-dimensional flat map, something fundamental has to give. The core reason maps are distorted is that there is no way to flatten a three-dimensional curved surface without stretching, tearing, or compressing some parts of it. Imagine trying to perfectly flatten an orange peel without any cracks or overlaps. It is simply impossible. This geometric truth, known as the theorema egregium by mathematician Carl Friedrich Gauss, states that a curved surface cannot be transformed into a flat surface without some form of deformation. Map projections are essentially attempts to minimize or manage these unavoidable distortions, rather than eliminate them. Therefore, every single flat map of the Earth will inevitably introduce some form of inaccuracy, affecting shape, area, distance, or direction. For instance, projections like the Mercator preserve shapes and angles well, making them useful for navigation, but they severely exaggerate the size of landmasses near the poles. Greenland, for example, appears vastly larger than it truly is compared to areas closer to the equator. Conversely, equal area projections like the Gauss-Peters accurately representing landmass sizes but distort their shapes. Understanding this fundamental principle helps us interpret maps more critically and choose the right map for the right purpose. When you are studying global population distribution, an equal area map will give you a more accurate visual representation of density. If you are navigating a ship or planning an aircraft route, a conformal projection that preserves local angles and shapes is far more useful for maintaining bearing. Cartographers develop different projections, each with a specific mathematical formula, to prioritize certain properties while accepting distortions in others. The ongoing challenge in cartography is to select a projection that best suits the map's intended use, recognizing that no single map can be perfect. This insight, that map distortion is not a flaw but an inherent consequence of translating a spherical world onto a flat plane, emphasizes the importance of understanding a map's projection before drawing conclusions from it. Knowing how Earth's spherical nature dictates these distortions transforms a simple image into a powerful tool that is understood through its limitations and its strengths.